So, what if your network had its own internal GPS? You know, a system that guides every single piece of data along the absolute fastest path, and it instantly adapts to traffic jams and closures. Well, that system is real. It's called OSPF, or Open Shortest Path First. And today, we're going to break it all down. See, before we had this kind of intelligence, networks are basically navigating with an old, outdated paper map. And in a world that's constantly changing, that's just a recipe for disaster, right? If a digital road suddenly closed, you wouldn't know until your data was already stuck in a massive traffic jam.
And this slide, well, it really gets to the heart of the problem that OSPF was designed to solve. It's all about the shift away from these older distance vector protocols, which is kind of like asking your neighbor for directions one turn at a time, just totally relying on secondhand info, to a modern link state protocol. And a link state protocol gives every single router a complete, live map of the entire network, so it can find the best path from a true bird's eye view.
So let's really dig into that old paper map problem. What were the specific issues that made it so darn unreliable? So the real problem with older protocols like RIP was all about speed, or really the lack of it. When a connection went down, that news just traveled so slowly from router to router. This slow convergence, that's the time it takes for everyone's map to get updated, caused huge problems. We're talking about routing loops, where packets just get sent back and forth forever, never reaching their destination. It just couldn't scale for the kinds of complex networks we all rely on today. Okay, so to fix all that slowness and those nasty routing loops, the networking world needed something totally new. And that brings us to the really elegant solution, OSPF, Open Shortest Path First.
Now, this link state idea is the absolute game changer. A link is just an interface on a router, and its state is just, is it up or down and how fast is it? OSPF makes sure that every router builds and maintains a complete map, a database of all these link states, so they all share the exact same, synchronized view of the network.
And this quote just nails it. Instead of asking for directions at every single intersection, OSPF gives every router that live network-wide GPS. It sees all the roads, all the potential traffic, and it calculates the absolute best path from start to finish before a single piece of data even leaves the starting gate.
So how in the world do all of these routers cooperate to build and then maintain these identical maps? Well, it's not magic. It's a very, very carefully choreographed process of communication.
This whole map building thing happens in 5 distinct steps. First, routers on the same wire introduce themselves to become neighbors. Then, they swap their local map info, which are called link state advertisements. Each router then takes all of these advertisements and pieces them together to build its complete map, the link state database. Finally, each router, all on its own, runs the shortest path first algorithm on that map to calculate the best routes from its own unique perspective. You know, what's really cool is how OSPF meticulously organizes all this information. It uses 3 separate tables. The adjacency database is kind of like a contacts list of its immediate neighbors. The link state database is the big one, the master map of the entire area. And finally, the forwarding database, that's the final, optimized set of directions, the routing table that tells the router exactly where to send packets.
In this process of becoming neighbors and syncing up maps, it's like a very formal 7-step dance. Routers start off in a down state, knowing nothing about each other. They exchange some greetings, they agree on the terms, and then they share their map databases piece by piece, all the way until they reach the full state. And only then are their maps perfectly in sync, and only then are they considered fully operational neighbors.
Now, this process works great when it's one-on-one. But what happens on a network like an office LAN, where you might have dozens of routers all plugged into the same switch? If every router tried to become neighbors with every other router, it would create a total traffic jam of update messages, just pure chaos. But OSPF has a really clever solution for this. Yeah, just picture a big meeting where instead of having one speaker, everyone tries to yell their updates to everyone else all at the same time. Nothing would get done. That's the exact problem OSPF needs to solve on what we call multi-access networks, like Ethernet.
So, to prevent all this chaos, OSPF elects a class president, the designated router, or DR. All the other routers on that network only form a full neighbor relationship with the DR and its backup, the BDR. They send their map updates just to the DR, and then the DR is responsible for efficiently passing those updates along to everyone else. It's a really smart hub-and-spoke model that keeps everything nice and orderly.
And this selection isn't just a random vote, It's a super strict, predictable process. The router with the highest manually set OSPF priority on its interface, well, it wins. If there's a tie, which happens a lot since the default is 1, the router with the highest router ID acts as the tiebreaker and it gets elected as the DR.
All right, so now that we've got the theory down, let's talk for a minute about a couple of fundamental concepts you would absolutely run into when you're actually setting up OSPF on a router. The very first thing an OSPF router needs is a unique name, and we call that its router ID. It's a 32-bit number, looks just like an IP address, and it serves as its unique identifier within the entire OSPF network. It's super important for things like that DR election we just talked about. A router has a specific pecking order for figuring out its ID. The best way, the recommended way, is for an administrator to just configure it manually. But if they don't, the router will look for a stable virtual loopback interface and pick its highest IP address. And if it can't find one of those, as a last resort, it'll just use the highest IP address of any active physical connection. So, once the router has its unique ID, you use the network command to tell it which of its connections should actually start speaking OSPF. This command is basically like flipping a switch on an interface, telling it, hey, start sending out hello packets, find some neighbors, and let's start building that map. All right, now for a classic OSPF gotcha that trips up so many people. To decide the best path, OSPF calculates a cost for every link, and lower cost is better. It uses a really simple formula, a reference bandwidth divided by the interface's actual speed. The problem is the default reference bandwidth is 100 million bits per second, or 100 megs.
Now this default was set way back in the day when a 100 megabit connection was, crazy fast. So you can probably see where this is going, right? What happens when we have links today that are way, way faster than 100 megabits per second?
And boom, here's the problem in black and white. Because the final cost has to be a whole number, any link that is 100 megabits or faster gets a cost of 1. That means a 100 meg link, a 1 gigabit link, and a 10 gigabit link all look identical to OSPF. The algorithm literally cannot tell the difference, which means it can't make a truly intelligent routing decision. So the fix, thankfully, is pretty straightforward, but it is absolutely critical. Network admins have to manually update this reference bandwidth on all of the routers in the OSPF domain to a bigger number that actually reflects modern speeds. This is the only way to make sure OSPF can calculate meaningful costs and make truly smart decisions based on how the network is really performing. So when you boil it all down, here's the key takeaway. OSPF is so much more than just a routing protocol. It's a system for building intelligence directly into the network itself. By giving every router a complete map and a powerful algorithm to read it, OSPF creates a network that is fast, resilient, and ready to scale. It really provides the foundation for powerful, modern network design. So the only question left is, what will you build with it?